precision methods of printing optical micro and nanostructures. Well, I don't remember how I managed that, but I'll try to say some words about that. Perhaps it will be a little bit about everything. So,
Может быть, на...
Мне кажется, ему просто нельзя было.
Okay, every time I will move there. If we are going to talk about printing methods, here I put the scheme of almost all printing methods, especially devoted to 3D printing techniques. It's additive manufacturing technologies. They can be divided into several groups. For example, material extrusion. These methods shows how you can print structures by continuous stream of material from the nozzle. Binder jetting and binder jetter and powder bed fusion, they both use powders as their base of printing, and binder use binder and powder bed fusion use local heating, and so on. Of course, I'm not going to tell about all these methods. It's too complicated and useless. I will show a few of them and show you some examples how you can use these methods if you want to print optical structures for optical application. Because all these methods are used in different areas like electronics, biomedical printing, and whatever. It depends on material, resolutions, and some local modifications for each application area. Okay, no, yes. First method is binder jetting. Its main material is powder. Powder which can be binded by any kind of solvent binder. So we have two tanks with elevator here and here. When we need to make a first layer, we use a roller to make a thin layer of powder on the top. Then the print head has nozzles with bind solvent, and we print the structure we want to the cross section of the 3D structure we want to get, and then the elevator in the main trunk goes down a little bit to make a new place for a second layer, and at the same time the elevator in the supporting trunk goes up, and the roller pull the next portion of powder to make a second layer. And so on, we print the 3D structure layer by layer. The problem of this method, the advantages, first of all, the advantages. It's a low price method, and it's quite fast for printing. And also, if you use different colors of binder, you can make a full color structure. Unfortunately, the main disadvantage of this method is roughness of your structure. Because here on the silicon powder, it's quite well seen that the small pieces of powder bind it together, but the surface is not really smooth. And of course, the binding is not really uniform binding this powder. So there is a deflection zone, and part of these powder particles can move out later because the binder is not really because it was not really well bonded with the other powder particles. That's why. Please. That's why we can use this method for optical applications. Well, at least I didn't find any article devoted to blind rotating, where we can print any structure for optical applications. It's connected, for example, I found some articles devoted to size of powder particles, and it turned out that most of them have size more than 20 micrometers. For optical applications, it's quite bad resolution. And that's why we move on. And we move to the group of polymerization. Polymerization method. It's the most preferable group for preparing structures for optical applications. The first method is stereolithography. It is the main material which is used for this method is different photocurable resin. So here you also see a tank with the resin, and here is elevator, which is moved only up and down, not generally down. Of course, it's usually used. It's moved by piezoelectric device, and so you can make quite thin layers, right layer by layer, with very good accuracy. On the top, we have a laser which writes each layer dot by dot. And advantages of this method are smooth surface. Of course, you can see that when we make a structure, we have a lot of extra material which is not used, and so we can reuse it, and also it can be usually that at least it was said that most of the resin can be recycled. I don't know, I didn't check, but they said that it's true. So disadvantages. Perhaps it's not really a big disadvantage, but you can use only one material. You can mix them. In this case, if you want, like in some other methods, we will see later, where you can use several materials at the same time. Of course, we are limited with the group of photocurable materials, and also some resin absorbs moisture, so they are hydrophilic. Now I'll show you few researchers which use this method for printing structures for optical applications. Of course, there's a huge amount of articles about different devices for optics. So I use just I put here just several of them. Here, two. In other methods, I used one perhaps, because I just took those I was interested in. Oh, I thought that is quite interesting. Perhaps you won't have a meaning. The first method, the first example is a 3D printer, 3D printed optical mirror with a nanometer scale surface roughness. So here the main point is that we use the method stereolithography, and the roughness of the surface is around 3 nanometers. It's a really good roughness. I mean, it's really smooth surface. So how they reached this result in this paper? Of course, we can't say that they move the elevator with the structure like for each 3 nanometers. Of course not. So the real roughness of the structure in the beginning, after we print it, it's about a couple of micrometers. But after that, the authors of the article, they used, of course, they have other steps like degassing in the vacuum, and they brush the surface of the mirror with the gel, and then they remove trapped air with vacuum, and also use spin coating to remove extra gel from the surface of the gel. So finally, the roughness of the final structure became 3 nanometers. So it's like 1,000 less than it was in the beginning. And after that, they covered it with metal, and that's how they received very good quality mirror. And this method allows you to fabricate any kind of structure, because complexity is not limited, and the shrinkage of the structure doesn't show itself, so there is no shrinkage of material further during the usage of this device. The second example which I put here is fabrication of photonic crystals for terahertz spectral radiation. First of all, I need to say that what's mean photonic crystals? Photonic crystals, first of all, it's a structure with a periodically modified refractive index. And second, photonic structure becomes photonic structure when its period is comparable with the wavelength which we use. If we want to make a photonic structure for the visible range, it will be about 100 nanometers. The period of the structure should be 100 nanometers. But if we want to use terahertz range, it's from 1.0 millimeter to 1 millimeter. So the structure, it's easier to fabricate such structure because you don't need a nanometer resolution. Here, the authors of the article, so yeah, the reference over here everywhere. They proposed the structure, which is around 1 millimeter, the size of the structure, and they printed it using stereolithography method, and measured the modeled and compared the modeled transparency with experimental. They matched quite well. Here you can see that in some terahertz range, the structure become totally reflects the whole light. That's because photonic structure doesn't allow exactly this range of terahertz wavelengths goes to the structure. It's the main point of photonic structure, to forbid light to go through the structure. That structure is used for wave guiding, for light trapping, and other stuff like that. If we are talking about optical applications. In the same group of polymerization methods, we also have digital light processing. It's a sibling technology to stereolithography. Well, they even looks quite common here, but the light goes from the bottom. Generally, it's not really important about the light. The most important differences here is that for stereolithography we use laser, and here we use projectors. So it could be lamps or just normal lamps. And if laser moved and wrote move and write point by point, here we project the whole. So we make cross sections of our 3D structure and enlighten the layer of resin totally by every cross sections. So generally it's faster than stereolithography, but stereolithography is a more accurate method. And also the other difference, well, there are some others, but well, of course, laser is more expensive than some simple lamps and masks. But generally for this method, we use such wonderful device called digital micromirror device. It's an array of micromirrors. Here is, you can see it closer. These micromirrors, they get a signal from computer, and they have two positions. When they direct the light from the lamp or from the laser, if you want, exactly to the lens and to your material, or if you or the second position, they direct light to any other direction. So the position is light on or light off. But it's not mean that you have only white and black points. You can also make gray points by it happens the mechanism of gray colors is that the mirror, which should show the gray color, switched to white and black position very, very fast. And the frequency of this switching shows different range of gray color. Well, quite good device. If you want to project some specific structures, this digital micrometer device used for maskless lithography. And if you use a lens which you can enlarge the picture, or if you use another lens, you can make it very, very small and around hundreds of meters. So it's really very useful. And here, there is a research about fused silicon glass. It's a very good material, and glass is generally a very good material. It has high quality characteristics. Unfortunately, well, before this research, fused silicon glass was harder to modify to make exact structures, complicated structures, because you need to work with the high temperatures. And here, authors of this article propose use stereolithography or digital wire procedure to fabricate any kind of structure for fused silicon glass. So how they did that? They mixed silicon oxide nanoparticles. They are around 14 nanometers with ultraviolet curable monomers. So what's a nanocomposition? Nanocomposite. And then they use, well, they say that it's stereolithography. I'm not quite sure because they said that they use commercial device, and at the same time they use digital mirror device. So I'm not sure which exactly this method they use, stereolithography or direct light procession. Anyway, they fabricated this polymerized composition, and then so they removed useless nanoparticle with monomers, and then they divided curing this composite into silicon glass with a high temperature. So it allowed them to make any kind of structure with this fantastic wood material. And here's other structures. They made microfluidic channels, or they did vertical structure. And here it was said that they use different intensity when they irradiate the nanocomposite with light. They use different intensity. That means that they should use here the red light processing method, because stereolithography method doesn't allow you to change intensity of the laser. It should be the same all the time. But it's also the difference between these two methods. So here I suppose they used DLP. And here also they used gradient intensity to make microspheres. Also with silicon glass and very smooth. That's also very important, smooth and with rough edges at the same time. So the resolution of these structures are really very good for optical applications. Here's my most favorite method, direct laser writing. It wasn't on the first screen, but it should be here. What's mean direct laser writing? Well, we focus laser in the particular spot of photoresist, and in this spot, we by focus and light, we initiate cross-linking of our material. So the main materials are photoresist and any photocurable polymers, monomers, and so on. The advantages of this method is that it's high resolution method. It's the highest resolution method which will be discussed today and which has existed for this time. Well, generally it doesn't need any extra software except maybe some post-exposure process. Disadvantages are, of course, that it's high cost. You need good lasers, well-stocked lasers, piezoelectric transmitter, and of course, if you print something dot by dot, it's always time-consuming, really time-consuming. And of course, we are also limited with some kind of materials, exact materials, which we need to use. Well, generally here is shown that we polymerize on the point in which you have a big intensity. I'll show it more precise. During laser writing, as it's commonly says, it's used to photon absorption. However, it doesn't mean that it's the only mechanism you can use to write these complicated high resolution structures. For example, we have an absorbance spectrum of our material. So the place, the wavelength where we have high absorptions, that means that here we'll have a good polymerization. However, we don't need that. Of course, if we will use the light with the wavelength in the peak of absorption, we can't focus in the particular spot. That's why we use two-photon absorption. That means that's a nonlinear effect, which appears when intensity of the light is very, very high. In our case, it happens when light is focused in the very tiny spot. So when the light of the laser goes through material, it is not high intensity enough to initiate polymerization. But when it's focused, the two photons can work as if it was one. And the energy is enough to initiate photopolymerization. So that's why two-photon absorption is a method that so we need a laser with a wavelength twice higher than the one-photon absorption. But also there is one more method which is called low one-photon absorption. You can choose the laser which is on the edge of absorption spectrum. And if you focus this laser in the tiny spots, it also, the intensity will be enough to start the polymerization. And here is the work of one of my colleagues who proved this theory and printed structures. For example, this spiral is the thickness of the spiral is around 500 nanometers, something like that. And so here also they measured the size of the spot they can focus. Also, you can measure it by different time of applying the spot for the particular place. And they measured the shape of the focusing spot. So this is one of my favorite methods. Here also another work devoted to two-photon absorption. Just very interesting research. Printing specific optical structures on the top of the output of the fiber. The reason to print something on the end of the fiber is light modulation, beam shaping, and some control of polarization of the light. For example, here, they made a specific photonic structure which makes the light left circle polymerized. So they just printed by direct laser light just on the top of the output of the fiber. So here the red is the fiber, the output, and here there should be output, and they they printed a ring to strengthen the structure, and in the middle there is a photonic small photonic structure around several 100 nanometers. And also they showed as an example different complicated structures like three independent lenses, so you can print the lens right out of your fiber, and you don't need to put it in the setup. So you can print all required lenses, polarizers, and other optical elements right in the end of the fiber if you know what you want. If you know what exactly you wish to get in the end of the fiber. It's quite interesting research, and I would say that, of course, they make an alignment so the light is goes directly in right position. Here is again the useless one. I just want you to show some other methods. So it's also based on the powder, and you can understand why it's not useful for the optical structures. Yes, because it's powder again. But here we don't bind powder. We use local fusion by direct laser writing generally. So laser writes the cross section a layer, and in the local places the powder is fused. So of course the advantage of this method is higher quality than for the binder tricking. Unfortunately, it's still quite rough. The stuff is quite rough. It's also high cost method, and requires some post proceedings processing. So here also I proved that there are some researches about polymer powder for this method. So and here on this not very well seen, but the size of the powder particles are also about 20 micrometers at least. So it's also useless. Next method is material extrusion. Material extrusion means that we stream our material through the nozzle all the time, continuously. This is the most simple method, the cheapest method, and unfortunately it has low resolution, and their materials, if we are talking about fused deposition modeling, is one of the methods of material extrusion. It used usually thermoplastic polymers. So here, somewhere here, there is a heating device which make polymer less viscous, but after jetting and extruding, it's become solid again. Also, you can use some materials which can be solidified rapidly after extrusion, perhaps under UV light, UV radiation. Or if the solvent evaporates fast enough to solidify the printed part. Of course, it could be used for waveguide preparation, or for example, for some. Well, I think waveguide is the most normal for optical applications. But well, I wanted to find a good example, but I found very interesting research, and I want to share it with you. It could be called, I'm not sure you can call it material extrusion, however, it has something in common. It's a 3D printing using stretching of meniscus of polymer solution. Why it's so key? Here, for example, we have some small, tiny optical elements, like nanorods, like here, nanorods, and if we are talking like photonic elements as a miniaturized copy of modern electronics, we need to connect our elements, like we connect electronics by wires. And here we use nanowire waveguides. The micro pipette have a polymer solution. Here is polystyrene, because it's used for waveguides. It's quite a popular material for the waveguides because of its high refractive index. And so the meniscus of the pipette touches the rod. And then we pull the pipette back on the top, and at that time meniscus stretches, and when the cross section decreases to nanoscale, it's rapidly polymerized because of the air. So then we just touch the place where we want to connect, and that's why we get a nanoscale, even if we have a micro pipette. Here we have a nanoscale wire, well, waveguide, and here they prove so they have the waveguide and two nanorods. Here the third one. So they irradiate this zone where is the first nanorod with the laser, and they store a signal from the connected nanorod. And you see there is no line between them. That means that there is no loss in this waveguide. And this nanorod is totally silent. That means that there is no leaking here also. And of course, if you want to make something like modern electro-optics, but using optical elements, we need multiplexers, and so they try to make the structure like that, and they show that it's absolutely possible to divide waveguides or smooth plastic. The last one, which I group of methods, the material jetting. Well, some of us are connected with this group of methods. Yeah. It differs from extrusion, where we stream our material continuously. Here we jet it by drop by drop. And of course, this method, well, as an extrusion method, allows us use multiple materials at the same time. Of course, well, disadvantage is limited material, and of course, we should remember about printability of jetability of our material. Here we are talking about rheological parameters of our solution. Well, we should know viscosity, density, surface tension. We have something else, and nozzle diameter to calculate. If we get into printable zone, this means that we can get stable drop for printing. Here I put a couple of researches to demonstrate this method. Well, this group of methods, because there is some small differences between them. I found this interesting research, which use drop by drop checking. Here you can see that the pin had jet droplets on the top of structure. And here, in the beginning of the structure, it is illuminated with the delay. This material is a hydrogel, and it can waveguide light inside itself. So the main point of exactly this method, this idea, is that when the drop gets on the surface, it's almost immediately polymerized because the whole structure emits light. So depending on the position on the top of your structure, you can find you can create any kind of complicated structure. Of course, you can, for example, you can drop here, the droplet here, and make it a second branch, or make something more complicated. This group will just propose this interesting method, like instant polymerization while jetting, while printing, and of course it's useful because you don't need to use extra UV radiation or something like that. And here I put the last, as the last example, the research of our scans group, because material jetting allows us to put into solution nanoparticles, any kind of nanoparticles, you know, And here we have optical spheres, which after solvent evaporation make a self-assembly structure. This structure is a photon crystal, generally, and of course it also forbids some wavelengths to pass this structure, and we can see different color reflection depending on the size of these spheres and on the incident angle of the light. So here our group printed different colorful picture using several. So here it was made three solutions with opal sphere of different diameter, and so they give different colors. And here is the picture that they printed and showed different angles. So earlier, the conclusion. As you can see, I put in the circle the most useful for optical diffusions method of printing, and most of them uses photopolymerization with liquid solutions, because these methods are have the highest precision. And those methods, which is also quite good, they use for fabricating bigger scale structures. And for example, these two, I didn't told you anything about this. It's laser and electric. I don't remember. Well, that's it's based on the melting of local melting of metals by laser or by electric beam. So you can make quite good metal structures, but it's not really useful for optical applications. Well, perhaps some, but specific maybe. I didn't find really good examples. So that's all. If you have some questions or discussions, or you wish to go. Where?
So I see DOD is the demand and G is material and G.
No, the optical JTB.
Where? This one?
No, on the top. Yeah, here.
Yeah, I think it's not optical jetting. The one is really. It's a drop on demand. I remember. Yeah, that's also quite interesting way of printing, but it's also useless for optical applications.
How it works?
Well, it's like if your material can be rolled like layer by layer, like thin films, which are cut layer by layer, and they are they stick to each other layer by layer, and you cut them in the right places, and that's why you make the 3D structure.
You cut them after.
So you pull the part, you cut, then you put the second layer, cut the place you need. Then put the second, so they like press and heat it. I'm not quite sure, and you cut it again, and then put the next layer and cut again, and so that's why it goes with it.
Another thing about perspectives of optical wavelengths fabricated by methods. Optical wavelengths.
Wavelength effects.
I've heard the efficiency is not really great for the time being.
Well, as you see, as you saw, the one I found, the 5%. All this research is like not more than 4 years, maybe. And the one which is the meniscus, I think it's a real cool one. So I think it really depends on exact applications and on materials, on setup, on the cost which you can afford your lab for fabrication and some other stuff. So
fabrication itself has no limits in terms of quality.
Yes, I think it's just maybe the question of time.